In this lecture, we are going to continue our discussion of convolution by looking at a totally different perspective on how it works. This is very helpful for understanding convolution, but it doesn't teach you anything new mechanically. So this lecture is optional if you want to move on and just learn about how to make CNNs. Something I mention very often is vectorization. We like to vectorize operations in code because using NumPy functions is a lot more efficient than writing your own Python for loops. The pattern you're looking for when you want to vectorize an operation is usually of the form of a dot product. A dot product is an element-wise multiplication and then the summation of those results. So whenever you see the sum over I of AI times BI, that's a dot product. This also applies to matrix multiplication, since if A and B are matrices, then the matrix multiplication of A and B is just A dot B. You'll notice that for convolution, we yet again have something similar. The only difference is that there are two summations. However, this is not really a relevant detail, since the outcome is still the same. Instead of summing over one axis, we're summing over two axes. But it's still an element-wise sum and add. The question is, why is the dot product important? One definition of the dot product, other than the element-wise sum and add, is that it's the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between A and B. We sometimes call this the cosine similarity or cosine distance, depending on the sign that you use. So how does this work geometrically? Consider just the angle for a moment. If the angle between the two vectors is 0, then the cosine of that angle is 1. That's the maximum value of the cosine. Now imagine that the angle between two vectors is 90 degrees. Then the cosine of that angle is 0. Finally, imagine that the angle between two vectors is 180 degrees. This is basically as far apart as possible. Then the cosine of that angle is minus 1, which is the minimum value of the cosine. So if you're just using raw cosine, then it's a similarity. The larger the number, the closer the two vectors are. The smaller the number, the further away they are. The maximum value when A and B are parallel is 1. The minimum value when A and B are anti-parallel is minus 1. And if A and B are orthogonal, then the cosine similarity is just 0. Okay, so why is that important? Consider now how you would find the cosine of the angle between two vectors. That's just A dot B divided by the magnitude of A and the magnitude of B. So I just rearranged the equation that we had before. Now, let's compare this to another popular measurement, the Pearson correlation. The Pearson correlation is defined as what you see here. But notice how similar this is to cosine similarity. The only difference is that the Pearson correlation uses mean subtraction. And so now you have two hints that convolution is really correlation. The first one from before was that we are actually doing what is called the cross correlation. And second, now you have that the dot product is actually very similar to the Pearson correlation. So I hope that by this point, you are convinced that the dot product, while it seems like an abstract concept, can be thought of as a correlation measure. It tells me how correlated is the first thing with the second thing. If they are highly positively correlated, then the dot product should be large and positive. That means two vectors pointing in nearly the same direction. If they are highly negatively correlated, then the dot product should be large and negative. That means the two vectors are pointing in nearly opposite direction. Finally, if the two vectors are orthogonal or at right angles, then the dot product should be 0. The reason why this is important is, you don't have to think of a filter as an abstract concept. In fact, it's just a pattern finder. This actually makes the term filter make a lot more sense. It filters out everything, not related to the pattern contained in the filter, by setting them to 0, and keeps everything that is related to the pattern. So what convolution is doing is, it's passing this filter along each point on the original input image and sliding it along. At each point, it asks, is the pattern here? Is the pattern here? Is the pattern here? And so forth. Then it gives us a high number in the positions where the pattern is found, and then a small number where the pattern is not found. And thus, this is your first alternative perspective on convolution. It's just a sliding pattern finder that passes through an entire image looking for a particular pattern.